ein paar Sekunden, ne? Man weiß nie, wenn das wirklich begonnen hat oder nicht. Also,
okay.
Ich habe 2 Fenster hier, um das zu kontrollieren. Es geht los. Nun, boa tarde a todos. Tenho o prazer de apresentar para vocês a palestrante de hoje, a professora Carola. Carola, she did her mathematics studies in Salzburg in Austria. She comes from Austria, and she finished her studies in 2004. Then she went to Vienna for her PhD. She started her PhD in Vienna and finished her PhD in Cambridge. After that, she went for a postdoc in Göttingen with Thorsten Hohage, I guess. And in 2011, she got a fellow of Jesus College in Cambridge. And in 2011, she became head of the Cambridge Image Analysis and Department of Applied Mathematics. And from 2015 to 2018, she became a reader in Applied Computational Analysis, also in Department of Applied Mathematics and Theoretical Physics. And since 2015, she is director of Cantab Capital Institute of Mathematics of Information in the Faculty of Mathematics in Cambridge. And since 2016, she is also director of the EPSRC, Center for Mathematical and Statistical Analysis and Multimodal Clinical Imaging, also in the Cambridge University. In 2016, she got an Alan Turing Institute Fellow from the Alan Turing Institute in British Library in London, UK. And since 2018, she is professor of applied mathematics at the Department of Applied Math and Theoretical Physics in the University of Cambridge. She got several prizes I saw on her CV. I think the last one was the prize from the Inverse Problems Academy community, the Calderon Prize last year. But the list is big, so I will refrain from mentioning all of them. And I will say hello to Carola, who talked today about hybrid mathematical and machine learning methods for solving inverse imaging problems, getting the best from both worlds. Thank you, Carola, for coming.
Thank you very much, Antonio. Thanks a lot for the kind introduction. So modern mathematical imaging is really about combining mathematical modeling, mathematical analysis with data-driven components coming from machine learning to solve inverse imaging, image analysis, image processing problems. With the idea behind, when developing new methods in this context, to bring together the best from both of these worlds. And so this is what I'm going to talk about today. Give you a few examples of how you can do that. So Antonio already said, so I'm a professor in applied math in Cambridge, and I'm head of the Cambridge Image Analysis Group. And then I'm also directing 2 centers in the Faculty of Mathematics. One of them, so Antonio actually spelled out the really long names of all of these, but let me give you the abbreviations because they're much easier to remember. So the first one is the CCIMI. That's an institute for the mathematics of information, so the mathematics for data science. And it's an institute that hosts both research and research training. So we are always looking for good PhD students. And then the CMIH is the Center for Mathematical Imaging in Healthcare. And that's an interdisciplinary research center where mathematicians, statisticians, clinicians, medical physicists, engineers, and so on are involved to develop new medical imaging techniques for analysis and processing of images. Okay, so this is the Cambridge Image Analysis Group. Consists of about 20 people. About half of those are postdocs, half of them are PhD students. And you can see that they have a lot of fun in what they do, at least on the picture. The research that we do is funded by a combination of of different sources. So research council funding, which means government funding, basically, private research trusts, and also industrial sponsorship. So what do we do in the Cambridge Image Analysis Group? Maybe one more thing to say is, you might have spotted, if you abbreviate Cambridge Image Analysis Group, and you say it, it's the CIA. And that was also one reason why we chose this name, which goes back to actually my first postdoc that I had in Cambridge. And so what do we do in the CIA? So we develop mathematical methods that range from partial differential equations, variational models, concepts that come from optimization and machine learning. We develop methods for quite a broad range of image analysis, image processing, inverse imaging tasks. So image reconstruction from indirect measurements. So think about computer tomography, MRI, and things like that. Image restoration, so denoising, deconvolution, in-painting is something I'll refer to later on. Image segmentation and classification, motion estimation and object tracking, and this is just to name a few. And we are developing these methodologies in the context of real-world applications that, again, touch upon quite a broad range of different areas. So photography, remote sensing, biomedical imaging, cultural heritage, so art restoration, forensics, and so on and so forth. So before I'll explain more about the methodologies that we develop, let me first explain a little bit what the challenges are that we face if we want to analyze images, if we want to extract information from images. And here I'm borrowing a concept from IBM research that they have defined a couple of years ago for what are the 4 V's for big data. And so now I'm borrowing this and say what are the 4 V's for mathematical imaging. So the first one is volume. So imaging data, as you can imagine, is very high dimensional. So it can easily consist of millions of data points and unknowns, therefore, that you want to process. It can also be, it can be large scale and high dimensional, which means it doesn't only need to be 2-dimensional, it can be 3-dimensional or even 4-dimensional if you think about time as well, if you think about videos. So this is a challenge for sure computationally. The next V is variety. So if you think about images is quite an abstract word, but the different instances that you encounter of images in the real world is extremely diverse. So what do we see here? We see here histology images. This is a CT scan. This is a photograph of an illuminated manuscript. This is something that I'll show a bit more of later. And this is a photograph of a bird. So this is a natural photograph. So it's very diverse, the kind of data that we have. And that means any kind of methodologies that we develop that should automatically, detect information, extract information from these images, this will be this methodology will be challenged by this variety. The other challenge is velocity. So with modern technology becoming more and more and more advanced, data is being acquired and imaging data is being acquired at increasing speed. And so one of the things this hits you both in terms of the velocity in which this data is acquired, means also the processing, the computations that you want to apply to this data also need to accelerate at the same speed. And the last one is veracity. And here, this is a light microscopy image here that you see. And what what I want to show here is, so veracity comes in terms of noise, corruption. So you have a lot of random corruptions in the data that your methodologies that you develop need to be robust with respect to this corruptions. These methodologies need to be robust. So remember the 4 V's, because this is something that we need to take into account when thinking about what kind of methods we want to develop. Okay, so once we have that now, what is it that we want to extract from such imaging data? So the common goal in mathematical imaging is to extract information from such, from such imaging data that is characterized by these 4 V's. And this information can come in several shapes and forms. And here I just have 3 examples. So it could be, for instance, think about you have a video where things are moving around. And before, on one of the first slides I've shown you about the work that we do in the CIA, I mentioned motion estimation as one task. So motion estimation means that you have a video and you want to quantify the motion in this video by computing from a video the direction in which things are going from one frame to the other. In terms, think of this as a velocity field, and the speed in which with which things are moving around. Now, what I'm plotting here is across a video sequence of, let's say, a minute or something like this. What I'm showing here is a histogram over directions which objects are taking when moving around in this video. So this is like a statistics about where on average things are going, okay, in which directions things are moving in this video sequence. And this is, for instance, important. This is something that we applied, by the way, for videos here of this Drosophila embryo, where the biologists wanted to know in which direction these microtubules in the generation of the Drosophila fly, this is a part of the generation of the Drosophila fly, in which direction these microtubules, which are highlighted here in terms of kind of white comets, okay, so they actually the biologists call these comets. These are because they use a particular marker in the acquisition of this microscopy image that just highlights the ends, the growing ends of these microtubules, which you can think of like spaghetti or something like this. Yeah, and by estimating the motion of this video, let's say over a minute, we wanted to understand in which direction these microtubules are growing. So this could be one information to extract. Another information could be, for instance, the task of land cover detection. So think about a satellite image, and what you want to understand from the satellite image is what are the different types of crops that are grown in this field. Okay, let's assume this is a farmer's land or something like this. And so this is a classification task where each pixel in this image, you want to say which crop it belongs to. Okay, this is another type of information you might want to extract. Another information could be what we call image segmentation. So this in image segmentation, you get an image, and what you want to extract from it are, well, you want to extract individual objects from this image to either count them or actually, if you segment them, you have much more information because you really outline the boundaries of these objects. So you can quantify the shape, the size, and things like this. Yeah. So this is something that you might think of a biologist could be interested in. Yeah. So this is segmentation. And so there are many more examples, but I'll just start with those 3. Okay, so now we have the data, we have the type of information we want to extract. So how do we do this? And so this is now going back to the title of this talk, which is about these two paradigms. So you have in mathematical imaging or in image processing in general, image analysis, and you can even extrapolate this to computer vision, you have these two methodological paradigms. One paradigm is what I call here the knowledge-driven imaging paradigm. So here, the idea is, so this is the mathematical modeling paradigm. You start with the data that you measure, the imaging data, and you start to define what the information is that you want to extract from this imaging data. And then you characterize the relationship between this information you want to extract and the imaging data in form of a mathematical equation. Okay, so very generally speaking. So if you can do this, if you can write down an equation that links the information you want to extract to the data that is given to you, and you can do this in a way such that the model in mathematical terms is well posed, which means you can actually solve this equation and you get a robust solution, then this is called the mathematical imaging approach. And these type of equations, these type of mathematical equations that you might want to solve, or mathematical models that you might want to solve, in this context are, for instance, nonlinear partial differential equations of this kind of type. These could be also phrased in terms of variational principles, variational models, where the information, you model the information as a minimum energy state of an energy which characterizes the kind of properties you're looking for in this information that you want to extract. And a lot of the things that we do is also how you represent this, how you represent the data, the measurements on the one hand, but also how do you represent the information you want to extract, and representation. So here the information I call the information U, okay? And again, this information we've seen before could be a segmentation, could be a velocity field for a video, could be a classification, things like this. So this information, I also to narrow down the search space for this type of information, I use a particular parametrization, for instance. And in the imaging context, what has been a very successful parametrization is what we call multi-resolution analysis, or the assumption that you can represent your solution sparsely in some kind of basis or some kind of dictionary. Okay, so this is just conceptually to show you a little bit what these mathematical methods, approaches are about. Okay, so this is this concept. The other concept, the other paradigm is the data-driven paradigm, where you say, actually, okay, I have my imaging data and I kind of know what I want to extract from this imaging data, but I really can't write down such an equation, or maybe I just don't want to. But what I have is a lot of examples of this information I want to extract from the imaging data, okay? And so where I'm getting at is that you have a training set. Instead of a mathematical equation, you have a training set. You have typical imaging measurements together with the type of information you want to extract. And then you start with a highly over-parameterized model, like, for instance, a neural network, and you train the neural network to extract this information, kind of teaching the neural network the kind of components, the kind of structures, okay, that it should look at in order to extract this information from, for instance, here, this is a classification of faces, to extract the kind of components, the characteristic components that usually the mathematical model models. But in this case, this model is totally data-driven. Okay, so thinking a little bit about both of these concepts, I'm mainly talking about the limits but I'll also get to the advantages in a moment. But let's start with the limits, or actually let's start with the advantages for the mathematical modeling problems first. So one of the advantages, as you can imagine, is if you start with a mathematical model that is well posed, you kind of trust in it. So this is a robust model. And also, since it's an abstract model, and it usually follows very generic principles, like, for instance, just to give you an example, think of edge detection. Edge detection, a mathematical model for edge detection would be, you take your image, okay, you take your given image, let's say U is my given image, and I look for places, so and I take the derivative of this image, so the gradient of this image, and I look for places where this gradient is large. Okay, so this is and this is where the edges are, where the intensity function of U is changing a lot, right? This is where the derivative, the gradient is large. So this is a very universal principle. This works for any kind of image, right? Doesn't matter whether this is a histology image or a natural photograph, or this is just a very general principle. So these mathematical models are universal, and hence they work they work universally. So this is an advantage. What is a disadvantage? A disadvantage is that these models can be computationally quite challenging. So if you think about it, so this is just usually these mathematical modeling approaches start, as I said before, this is just going back to what I said before, you have your measurements that I call here Y, okay? You have your imaging data Y, and you have your information U you want to extract, and then this is the model that kind of connects the two. Capital T is just a very abstract model for the relationship between the two. And then little n stands for all kind of corruptions that you might encounter when looking at these at this imaging data Y. And then a typical mathematical modeling approach to computing U from Y is this variational modeling approach that we've seen before, where you capture all the information you have about U that you want to use in order to extract U from Y, in terms of an energy functional, for which the desirable information, the desirable U, should be a minimum of. Okay. And so one typical thing, for instance, could be to say, on the one hand, I want that my U kind of solves this equation. So this is my least squares fit. But actually, just solving this equation would not give me a well-posed mathematical model. So I need to complement this with some additional information I want to use in order to narrow down the search space for this information. And this is taken by this other term here, which has a kind of regularization effect. Okay, so this is narrowing down the search space and says, actually, I'm not just looking for a U, which kind of, approximately fulfills this equation here, but I'm also looking for a U who's who has a small L1 norm of the gradient. And that, very roughly speaking, without going into details, means, again, going back to this thing that I said here about sparsity, this means I'm looking for a U which has a sparse gradient. So the L1 norm models sparsity. If you minimize the L1 norm, you get a sparse solution, and in which kind of representation this solution is sparse depends on what you put here into the L1 norm. And in this case, I put the gradient, which means I assume that the image has a zero derivative in almost all places, and just a non-zero derivative at the characteristic places where edges are. This is a very, very popular type of narrowing down, model that mathematicians are using. Okay. Okay, but I'm saying too much about this. The important thing is that what we need to do in order to solve something like this is that we need to solve a very high dimensional optimization problem. And for those of you who have done any optimization, they know what this means. Can be computationally extremely heavy. I mean, I said before, images can have millions of unknowns. And then even worse, again, if you've done some optimization, you might spot that I have in my optimization problem, in my function, I have a non-smooth term that I can't differentiate. So gradient descent or something like this will not work. So all of this is very challenging. So these are usually these are very non-linear problems that you need to solve. No one-fit-all solution. Look at all these images. A sparsity assumption, like the one, saying that my information is sparse in terms of the gradient of hue. I mean, this is, on the one hand, it is universal. On the other hand, it's a very, very simple model for the different types of images that we are looking at. For sure, if I'm looking for a sparse gradient here, I will not get the right thing. Or, think about here, if I want to detect the spot in these images, for instance. So these are, the type of images are very different. So the kind of mathematical models that are to my disposal are too simple for the kind of image structures that we encounter. Deep learning, on the other hand, and here I'm not showing you again examples, because I'm totally sure you have seen a lot of deep learning examples and you have all been amazed what deep learning can do. Deep learning is very, very good in modeling images. It's very good in modeling images, and that's why it is so successful. What is a bit concerning for a lot of people who want to either use or develop these image analysis approaches based on deep learning is that it's a black box. So you don't really know how it's doing how it's doing what it's doing. There are almost no, I would say. So here, for those of you who are interested, I don't know if Antonio will share the slides with you afterwards. If for those of you who are interested, you can look at some of these references here. There are people who are thinking about the mathematical underpinnings of neural networks, but it's very few that you can say. And the things that people can say is maybe for 2-layer networks or something like this, very, very simple kind of models. So there are no theoretical underpinnings, and there are also these non-robustness examples that we know, these adversarial examples, where you perturb your imaging data a little bit, and all of a sudden your classification is totally something different. And now imaging data is very noisy, right? So the kind of imaging data that we really encounter in the real world. So this is a bit of an issue. The other thing is neural networks are bad at extrapolation. They are trained on training data, but they're not very good in actually going much beyond the kind of data that they have been trained on.
Carola?
Yeah.
There is a question. Mateus wants to know whether edges are high frequencies areas in an image.
Yes, exactly. Very good. Yes.
Okay, thank you.
Okay, so summary. We have knowledge-driven, we have data-driven imaging. Both of these have advantages and disadvantages. And what we really want to do is we want to somehow understand what is it that we require of both of them, maybe, to solve the kind of imaging problems in the wild. Okay. So again, thinking back, real imaging data is complex, it's diverse, it's messy, and the information in it can vary tremendously and unpredictably. So what are the requirements on the tools, the methods that we are developing? Okay, so the one thing I said before was we need to be robust to data corruption. Okay, so this is for sure something we need to be. I, for instance, collaborate a lot with people in in the hospital or in medical research as well as in the clinic. So there, it's crucial that you have guarantees that if something in the machine gives you a slightly different type of noise, that you don't totally screw up your prediction that you make on the basis of this data. We need extrapolation. We need extrapolation because in a lot of the things where imaging is used, think about scientific imaging, think about material sciences where people are using electron microscopy to look at things which they couldn't see, which are so small they couldn't, you couldn't see it otherwise. You need to trust the kind of image processing techniques you apply to the data. You can't check it. You don't have a training set. So you need to be able to go beyond what you have seen before. But then also you need to be sufficiently accurate. And deep neural networks, again, because they are so good in modeling prior information, they can be really, really accurate. And this is also why they have been very successful and why we are also excited about them. And these methods also need to be computationally affordable. Another thing is with neural networks is that once they are trained, they're computationally much, much more efficient than any of the kind of, well, maybe I shouldn't say any, but a lot of the kind of things that Antonio and I are solving as our daily bread. Yeah? Okay, so this is where we want to be. We want to be somewhere in the middle. Physical constraints. So we want to have interpretability. So we want to understand what is happening. We want generalizability. So we want extrapolation. We want, on the other hand, to be accurate, to be adaptive to the data. Okay, the insight and the structure, we just said. We want guarantees, we want robustness, and we want computational efficiency. So is this a dream? I'll show you some examples where this is not totally solved. So it is still kind of a dream, it's still kind of a vision, but we are making baby steps towards this vision. Okay. So without burdening you too much with lots of different things that you could do, I thought I'll pick out one example that is also kind of nice for Friday. I mean, for me it's Friday evening. For you it's a bit earlier, but still it's kind of nice way to kind of end the week, and that is the work that we have been doing on art restoration, on cultural heritage, art conservation. Okay, so here I'll show you work that we did in a kind of very interdisciplinary team between mathematicians, art historians, and also conservators, so the people who are actually physically restoring paintings and things like that. Yeah. Okay, so let me explain so this is just a teaser here that is running through, but let me explain to you what we are doing here. And this collaboration started maybe about 5 years ago or something like this, and this was one of the first things that we did. So what you see here is a detail, is an example of an illumination. And so so illumination, when I say illumination, I don't know how common this word is. I mean, I'm originally German speaking. I had no clue what this meant until someone explained it to me. So illuminated manuscripts are manuscripts where they have painted with gold and stuff like this in the manuscript. So there's writing and stuff like this, and they have used gold together with other materials to do the painting and the writing. So this is what is meant by illuminated. Very very roughly explained. Okay, what you see here is a detail from a manuscript from the 16th century that is a primer. So it is so a primer is the following. It is a book for a child. It was made for a child that should teach the child the alphabet. So this is what is called primer. And at the same time, so it's teaching the alphabet by telling the biblical story of creation. Okay, and so what you see here, for instance, is so you see Adam and Eve, Eve being born out of Adam's rib, for instance. You see here God instructing the two of them what to do and what not to do in paradise, and things like this. Okay, so this is what the content of the book is. So now, if you look at this, so one thing that this whole story started was that I said we are developing methods for art restoration. So if you look at this, looks pretty good actually, right? It doesn't look corrupted or damaged or something like this. But then the people in, so the Fitzwilliam Museum, by the way, the Fitzwilliam Museum is our university museum in Cambridge, okay? And so in this museum, they have also scientific imaging techniques, and one of these is a spectral imaging technique. Okay, so what you see here is, so this is basically just a photograph, shows you the visible light spectrum is an RGB photograph. What you see here now is an infrared image. So there are sensors, photographic sensors, which can go beyond just the visible light, but can cover a wider light spectrum and filter out the different components in this light spectrum. And what you see here is the infrared band. Okay. And so one interesting thing when you look at this now is that you can actually see structures underneath the skirts of Adam and Eve. And so this kind of confirmed what the art historians already suspected, namely that this manuscript has been altered, has been changed at some point during its lifetime. And it has been changed, being handed over to an owner sometime, later on, when kind of, when showing people naked in books to a child was not the thing to do anymore, basically. And so they have been given skirts. And so now you can imagine, what they wanted to do. What they wanted to do is, so one thing to say also is that these illuminated manuscripts, they would never touch them physically, right, and remove the skirts or something like this. So first of all, they don't want to change history, but then also with illuminated manuscripts, it's even there is even a second reason, namely that the pages are so fragile that by doing something physically to them, they are in danger of actually breaking them. So actually the common practice nowadays for illuminated manuscripts is that they physically don't do anything. So what we wanted to do is to have a digital mock-up of how the manuscript could have looked like before the overpainting has been committed. Okay, so how do we do this? So the first thing we do now, thinking back to the whole story I told about imaging methods, image analysis methods before, the first thing that we do is to try to formulate, first of all, what we want to do in a kind of mathematical way. Okay. So what we want to do, if you go back, what we want to do in a way is we want to, just looking at Adam, we want to take this skirt, get rid of it, and replace it with something that is kind of suggested by the surrounding, right? We kind of want to, instead of having the skirt here, to have skin color here and stuff like this, and maybe here have some part of the background and stuff like this. Okay. So the problem, the image processing problem that is closest to what we want to do here is what we call image interpolation or image inpainting, which is you have an image and there is part of this image, which is in our case Adam's skirt, where the image, the original image information is lost. Okay, in our case is overpainted. And what we want to do is, given the image that I call here F, sorry, I'm changing notation a little bit. So here, the given image is F. And what I want to do is I want to use the information that I have of the image here outside of this domain to reconstruct F inside, okay? So that is what I want to do. All right, this is called image painting. So how do we do this? So the interesting thing is the kind of first works of applied mathematicians on the image painting problem happened here about in the 90s, but actually I think the one that I'm referring to here is the work by Marcelo Bertalmio from 2000, where what Marcelo and co-authors, how they started, approaching this problem was to say, okay, so how do we actually model this? How do we interpolate images? And so what did they do is they talked to people who are doing this for their living, namely to conservators, to people who are actually restoring paintings. And I'm calling them here museum artists, okay? So people who are actually doing this physically. And what they got from them is actually a very, very simple principle that might be, again, quite intuitive, is, so how do they do this? Again, looking back here, what they say is, well, okay, so we look at the structure, at the color and so on, and the surrounding, and then we propagate it. And we propagate it along edges, basically. So we try to propagate it along edges, or what is a bit more general than this, they are interpolating contours of constant grayscale or of constant color, okay? So this means you have your in-painting domain, you look for colors that are arriving at each of these sites, and you try to connect them in a way, yeah? And you can model something like this with the partial differential equations. And for those of you who have looked at partial differential equations before, you can think of this as a combination between, so most of the PDE approaches to in-painting that people came up with are combinations of transport, so transport mechanisms and diffusion mechanisms, okay? So transporting color and diffusing it, yeah? Okay, so let me show you the result without going into too many details. Because one other thing to say is, of course, so now I'm zooming into Adam here. One other thing to say is, actually, we have a bit more than just the color information here, right? We actually also have structural information underneath this skirt. We have edge information underneath, and this is another thing we want to use, and this is what you have seen before also in the teaser. Okay, so what we now want to do is we want to take this color information and use a differential equation that I'll show you in a moment to propagate the color inside the skirt by a kind of diffusion transport process that is guided by the structure that we have here. So basically, this means skin color should not cross these boundaries, for instance. Skin color should go here, and the background should go here, and things like that, okay? And that's the result. Okay, and this is the PDE that we used for that, has been proposed by Joachim Weikert in 2013. It's a drift diffusion equation where inside of this vector field D is basically this information, or this edge information that I've plotted here, okay? So what do you see? You see is that, well, it's doing kind of the job, it's propagating the color, but it's also making Adam a bit younger, right, here underneath the skirt. So it's a very smooth thing. And this is the typical thing of these differential equations, that they are local smoothers, right? They capture local correlations. Okay, so what to do? We can't leave it like this. This is the art. Our collaborators in the Fitzwilliam Museum did not like. I mean, they kind of were, kind of nice to us, so they didn't say it like this, but they didn't like it. So what do? We go to something else. So we made a first step, but now we need to get the texture somehow. These patterns and stuff. And we also need to get them inside. And here we actually went back to a kind of machine learning approach. Okay, so here, this is a totally mathematical model-driven approach. I take this PDE and I solve it. In order to get the texture, we now need to do something a bit more data-driven. We need to look a little bit here at examples of what could be here, and the approach that we take is the one which copy and pastes this information inside of the missing domain. So how, just very briefly to explain this, the idea here is you have a source region, which is everything outside of Adam's skirt, and you have a target region, okay, which is the skirt, which is Adam's skirt. The idea is you start somewhere at the boundary of Adam's skirt. You look at a patch, so not just at an individual pixel, but you look at a collection of pixels, and you look for similar patches outside, where you compare, of course, if you take a patch at the boundary, you compare the part which is in the visible domain, so in the domain outside of the skirt, and you look for similar ones, and then you just copy and paste, and you go on like this. Okay, so this copy and paste procedure is fragile with respect to guidance to initialization that is given here by the structure. So the good thing was, what we did is we applied this copy and paste procedure, but constraining it to the structural result that we already got, okay? And then you actually make Adam a little bit older and a little bit more realistic. And this is the result overall. So this is applied to this one detail, okay, in the manuscript. And this was actually exhibited in the Fitzwilliam Museum. So this is also the cool thing about doing this kind of mathematical imaging. Because yeah, so actually you reach a very, very wide audience with this, and it's also, I mean, for yourself, it's visually very pleasing. And we got even into the newspapers. Look at this, and the title was quite nice: Adam and Eve naked again after centuries old cover up. So yeah. Anyway, so, and this is only the beginning. So we have actually a project now where we are looking at different applications of such image in-painting approaches to do, not just get rid of over paintings, but also really cure damages like this one. Here you see these damages highlighted and then in-painted and stuff like that. Okay, so this is something that we do. One last thing, and then I finish, to say about deep learning, okay? So we did, because this is maybe something that comes to your mind now that I've shown you this image in-painting problem. So deep learning would be great if we could apply it in this context, but we at the moment can't. And the reason is that we don't have enough training data. We don't have enough training data because you can imagine these historical books or paintings, there's a limited number of them. And the art historians, they don't want us to train models on something completely different, on different artists, for instance, okay? So they don't want us to do this because they don't want us to reproduce something that has nothing to do with what is actually there. So they want to have a logic behind and a relationship to the piece of art that the method is also making. And therefore, deep learning is kind of failing at the moment because we don't have enough training data. This is just showing you one deep learning result that we got with this limited amount of data, okay? So this is really the crucial point for removing here this crest, okay? This is another overpainting that has a story behind that I'm not going to tell. But so this you can see there is a bit, this is the trouble here, that we don't have enough training data. And we have a project on this. So if you want to know more about this kind of art restoration, go and visit this page. And with that, I think it's time to finish. So let me just say again, well, without the Cambridge Image Analysis Group, this really would not be possible. Oops, why am I here again? Oops, sorry. Okay, 1 second. I think I set the link wrongly. Sorry, exactly this I wanted to avoid. Very sorry. Right. So takeaway messages. Mathematical methods offer a really powerful and rigorous toolkit for imaging. They're very tough to solve. These are these non-smooth optimization problems, very large scale, or nonlinear PDEs. They're quite tough to solve, but they come with guarantees and they're very universal. And we have seen the kind of cool things that they can do even on this in this art restoration example. Machine learning, on the other hand, is a powerful adapter to the data. Okay, so with this very low level machine learning approach, with this copy and paste approach, we could actually regenerate texture inside of this missing region. So it's really the combination between the two, I think, where the future lies and where also the interesting questions lie. There are several cool applications, and there are many open questions in both the theory behind these approaches and also the application. So I thank you very much for your attention. And yeah, thank you.
Hi, Carola. Thank you very much for the nice talk. Let's wait for the questions from the audience. Meanwhile, I have a question myself. So when you were talking about the in-painting method for ADAM, for instance, usually when you use neural networks, you have a huge amount of data that you use to train the network. But I understand that in this specific application, you are allowed only to use information from this picture. Is that so?
From this picture, or so here in this case, we could use it from the whole book, let's say. Yeah. But these are still quite few examples in a way. But yeah, so the art conservators really don't like this idea of us training the in-painting approach on photographs of cats and dogs or something like this, or even other kind of illuminated manuscripts. They like, behind the kind of mathematical approaches like the differential equation, what they like is that they can explain how this works. What are the mechanisms that are used in order to do this propagation of color? If they use a machine learning approach where they use structures that come from the same artist, from the same image, let's say, or even from images from other images or other paintings from the same artist, they can still explain the relationship in a way. But if you use totally different images and then you use a method like deep learning, then they can't explain it and they don't really like that.
Yeah, I see. It's interesting because neural networks, they work with objective function. You have something that defines the cost of the problem that you are trying to attack. So and how does this cost functional works in this specific problem of the in-painting for Adam, for instance, or for the other picture that you showed us?
So in this case, for this approach that I showed you, the copy and paste one, it works like this, that you compare that the cost function is a similarity between patches. So that is, but that is not the deep, this is not the deep learning approach. So with the deep learning approach, you just have well, the loss function depends on the in-painting approach that you're using in this deep learning context. But one example for a deep learning based in-painting loss that is very, very generic is just, again, a mean squared error. So you compare with a ground truth image, so you basically cut out something from an image, then you try to in-paint it and you compare it with the ground truth in some norm. For instance, again, an L2 norm or something like that.
You see, for instance, I have always in mind these classification problems. So classification problems are problems that you have the data and you know the solution. You know the classification for the data, but this is not the case for these problems, this in-painting problems that you're showing us.
Yes and no, but so what you would do if you try to train a model, you would look at intact parts. You would look at parts of the image where there is no real damage, but you damage it artificially.
I see.
And then you train on this made up training set.
Interesting. It's quite interesting, and results look very good. So, congratulations. So far, we have no questions whatsoever. I think the students are scared by having a so famous speaker in our.
Nah, they should not.
So, Carola, it's almost 3 o'clock, so I think we should finish. Thank you very much for accepting our invitation and for giving us this wonderful talk this afternoon, this evening for you. And it was a pleasure talking to you again. So let me say farewell to our audience, and let me just advertise that next week, let me say it in Portuguese. Na próxima semana teremos a próxima palestra aqui do colóquio, e vocês estão convidados a assistir a palestra do professor Cleverson aqui do departamento. Ele vai falar para a gente na próxima sexta-feira. So, Carola, this is it. Thank you very much. I will finish the program. Um abraço a todos. Até a próxima semana.